Alright, hi everyone, welcome to my YouTube channel, City of Electrons. Now, in this video, we are going to talk about this. What is this? Example on common emitter fixed bias. Now, from our previous videos, we are going to apply what we've learned. So this slide is from our previous video. So the knowledge or the ideas we've established in this slide, which is the previous video, we are going to apply them in this example of common emitter fixed bias. Okay, now the first thing to bear in mind is, why is this thing even called common emitter fixed bias? Why is it correct? Why is it correct to say this is CE, common emitter fixed bias? Now that's because, of course, this is our collector pin, our base pin, and then our emitter pin. This is the input, right? VI, voltage in and voltage out. You see this emitter pin, it is common to the input and the output. So since the emitter is common to the input and output, it's called common emitter. Okay, common emitter bias or common emitter configuration. Configuration just the method in which this transistor is wired. So the way the transistor is wired determines the name of configuration. So configuration just means different wiring. Okay, so now looking at this, we can see that the transistor is wired in a way the emitter is common to the input and output. So it's common emitter fixed bias. Okay, now with that being said, let's see what's up with this example. So we have this, and then this guy is here. It just means this input signal is inverted. Okay, you can see this, and it comes this way. The input signal, the output signal is the inverted form of the input signal. That's just the meaning of these guys here. So now, for the network above, determine RE. Find this. So I will read each one and solve instead of to just read the whole thing. So let's deal with question A. Okay, now we are asked to determine RE. Okay, what is RE? We said this in the previous video, that RE is the same thing as 20, let me just put it, same thing as 26 millivolts all over IE. We said this in the previous video, and we have it here in our solution. Okay, so let me just work with this here, our solution. Now, if you look at this problem, you see from B to E, you see RO as infinity. Okay, then at F you see RO as 50 kilo ohms. That means we have two cases. Case 1, RO equals infinity. Case 2, RO equals 50 kilo ohms. So what we are doing is, from A to E, we are solving with RO as infinity. So these are the parameters given. And then these are the parameters given. I should have included these values in this diagram here. I should have done that, but just note that these values are coming from the question. I should have included it in that part. So let's just continue. Now, exactly the first thing I said, recall that RE equals 26 millivolts divided by IE. Now, what we have to do first, is to look for the value of RE and substitute into, is to look for the value of IE and substitute into this RE. We get our RE. Question A solved. Straightforward. Now, recall that IE, now I will explain why we have this thing like this. Okay, but IE is as a result of IB plus IC. Okay, why? Because this is IE here now. Okay, the current at your emitter is the IE. So whatever current that that we see at IE is as a result or a sum of the current from IC and the current from IB. That will, the sum of this current will result in what you have in IE. So that's why you have this expression here: IE equals IB plus IC. Okay. However, there is a relationship, a special relationship between IC and IB, and that is this: IC equals beta IB. IC equals beta IB. I think this is the only thing we just have. This is one of the things we have to memorize. Okay, just put back, side, front, everywhere of our mind. So side of our mind, first of our mind, back of our mind. Now beta IB equals IC. Okay, so we can substitute this thing into this equation. I think we did this in the last video also. So that will result in excuse me, so that will result in IE. I think I have an expression like that here in this place. Yes, I did that here. That's good. So we can see it already. I've done that already, thank God. Okay, so when we substitute in this value, we have it here. So instead of writing IC, you write beta IB, and then we just factor out IB. Okay, so when you remove IB from here, you have 1 left. Remove IB from here, you have beta left. So you have beta brackets 1 plus IB. Okay, so this is what you get. So that means IE, okay, IE equals, what is our IB? What is IB? Okay, now we have to find IB. Okay, we have to find, beta is given in the equation as 100. Look at it here. Beta is given as 100, but IB, we have to look for it. Now, before we get to this point, how they got IB as this thing, we did this thing first, right? So how did we get this part? Now there is something we have to do. IB is located here. Okay, IB is because the voltage across this point is IB RB. That's the voltage across this point from Ohm's law. So since that's the case, we can use, to find IB, we can go from VCC, that's the supply, to the voltage to this part. Are you seeing the part? If we take from the base to emitter part, we are going to get what IB is. So from base to emitter part, we have 12 volts. That's voltage drop. So 12 volts coming in, and the voltage drop here will be what? IB. The voltage drop there will be IBRB. Okay, then the voltage drop here, that's VBE. Okay, I didn't place, let me do this. This is C collector, collector, base, emitter. So the voltage drop here is VBE. Okay, so let's put it there, minus VBE, and then at this emitter part there's no voltage drop here, so equals 0. Okay, equals 0. So now equals 0. This is what we are going to resolve to make IB subject formula. And if you do this, you have, or should I put this as VCC first? VCC, which is the same as our 12 now. VCC. Okay, so VCC minus, oh boy, this you're writing. VCC minus VBE. So we take IB to the other side. I will subtract from both sides of the side. Okay, so this will just happen. We'll just move this guy over, and then of course we divide both sides by the RB. So what we'll now have left is what? Let's just switch sides. VCC minus VBE all over RB. Okay, so I just switch side, bring this guy this way, okay, bring all these guys this way. So this is the expression we are going to have. Okay, so IB, the value of IB is this. Look at it, that's what we have here. Exactly, going. All right, so we just have to put in the value. What is VCC? VCC is 12 minus 0.7. Why? This is the value for VBE. Okay, it's like a constant value. Okay, there's a range. However, most times we just use 0.7 once here VBE, being that the silicon, the material used there is silicon. Okay, or kind of default approach. So just know that once you see VBE, know you are using 0.7. Okay, then divided by RB is what? RB. Yeah, 470 kilo ohms. So we have it here, 470. Of course, this just means kilo. Okay, so when you do this, you get IB as this, right? Good. Now, back to this expression I gave earlier. This one, we just substitute in this guy, okay, into this part where you see IC, put beta IB. Hope you are following. Please follow. You can pause the video, take it back, things like that. Okay, so here you see IC, put beta IB. Then you just factor out IB, you have this. So IB, we've already solved it as this. You plug it there. Plug 1 is 1 now. Beta is 100 in the equation. Beta is 100. Okay, so that is what you get, and then you do your arithmetic and you arrive at this. So this is IE. Now we can bring in the value of IE into RE, and when we do that, we have this. So if the pattern comes like this, it's almost like this is the pattern. We are looking for RE, but we now find, but we need IE to get RE. To get IE, we need IB. Are you seeing the pattern? We are asked to look for RE, but to get RE, we need IE. To get IE, we need IB. So that's just how the process. That's how we moved just now. So we take this value, we solve for this value, following base to emitter parts, get the answer, bring the answer to this value, get the answer, bring the answer to this value, get this answer. Okay, so that's for A. Then for for B, we are asked to look for ZI. Okay, now to look for ZI, what we do is this. There is a diagram I'm supposed to draw. I just recall I'm supposed to draw that diagram, which is the RE model, okay, which I talked about in the previous video. Or I think I should just copy it and bring it here because it's the same thing. It's the same thing. Yeah, this is it, the RE model. We did it in this video here, so I'll just copy it and bring it over to what we have here. We need it. We need a more. Okay. Where do I drop this boy now? So the RE model should be somewhere close enough for us to see, because we need it. Yeah. I think that's good enough. So let's just. Okay, now that we have our RE model there, so what we are going to do is this. Now we need the B part, we need ZI, okay, which is the input impedance. Now this input impedance, if you look at it, okay, of course it is the sum of all the impedance in the input side. And what we have here, we have RB and we have beta RE. These are what we have as the resistance here and the resistance here, and they are parallel to each other. This RB should be in capital or small letter, whichever one. And since we've done this in the previous video, why is this thing beta RE? We did it in the previous video. Why is this? We did it. Okay, so just check out those videos. Okay, now, or that video. So now we can see from that RE model why RB is parallel to beta RE. Okay, and beta RE, of course, beta is 100, RE we've solved for RE. So you just put their values there. RB is 470, right? Look at it, 470. Then RE we solved for it, that's it there. So you just substitute in the values and do your arithmetic, and there we have it. Okay, then for the output impedance, we said it's equals RC. Why? Recall, this one I just have to go back to the slide so I don't write the whole thing again. Recall, we said in the previous video, where is that guy? Yeah, here we said in the previous video that RC is parallel to RO. Look at it now. RC is parallel to RO, just like we did for the input side. This parallel to this. For the output side, this parallel to this. But the thing is this. Okay, look at it. But the thing is this. We said where RO is very large, 10 times larger than RC, and of course that's the case we have here in case 1. Where is it? Case 1, RO is at infinity, equals infinity, so it's very large. That means what we will just have is RC. Where is that guy now? Yeah, it's RC. So you see why this case 1 we just say ZO equals RC. Okay, so that's for that. Then for D, we are looking for the voltage gain, and of course voltage gain equals minus RC all over RE. We also did this in the previous video. Remember that previous video, Bob? We did a lot, so we've done a lot. So we also explained, or we solved and see why we got it as that, the voltage gain, in the previous video. Okay, so the same thing. So we just come here and continue from that point. Okay, so where are we? Yeah. So RC is what? Look at it, RC. Okay, so the minus sign will be there, of course, and I explain why I'll put the minus sign. And then RE, we've gotten that already. So we'll just plug in the values, and this is what we have. Then for gain, current gain equals beta, or this value. However, current gain, look at it here. Current gain, we have that as this expression. Look at it, this expression. Okay, this is the expression we have for it. But for the fact that RO is very, very large, current gain will be reduced to this. Okay, so you can just write this as your current gain. Beta equals beta. Okay, current gain equals beta, or you can say this as your current gain. So you plug in the value. AV, we already have it as this. ZI, we already have it calculated already as this, and then all over RC. You can just say current gain equals this, and you put in your answer, or you want to do it like this, whichever way it works. Now in case 2, in case 2, where we have a value for RO which is 50, now the effects will begin to show. ZI, look at ZI will remain the same. Why? Because there's no RO here. so it won't affect zi. No wonder in the question we were asked to repeat from C to E. They didn't ask us to repeat from B, neither A, not even A, because arrow O only has effect on this guy. And once arrow O has an effect on this guy, difference creates a difference. Once arrow affects this guy, it will also affect this and this. Okay? So now let's go. So since we have arrow now, so we'll now take it in parallel. Same formula, and then we'll have this value. Just plug in the values. Arrow C is this, arrow E is this, and then parallel, just plug in and get that. Since we now have a new ZO output impedance, that means our voltage gain will be different, because there will be a different value here. So you plug that in or substitute that in, and you get this as your answer. And then of course your I will be different. Of course your current gain will be different. Of course. Why? Because of this. Look at it. This part we said current gain equals beta, because RO was at infinity. Now RO is no longer at infinity, it's at 50 kilo ohms. Therefore we have to apply this formula, okay, which we are applying right now, which we are doing right now. Okay, so this is it. All I did here is just to multiply and open the brackets. This guy should remain in the brackets, this guy should remain in the brackets. Here we just multiply the top, and then we substitute in the values. Beta is 100, beta is 100, RB is 3 kilo ohms, RO is 50 kilo ohms, and then we just plug in the values at that and carry out the arithmetic, basic arithmetic, plus and minus, times and divide, and we get this as the answer for our current gain. Okay, now that's the complete solving for this particular question. Man, so I really hope this helps. Okay, now if looking at this video or watching this video, you see I moved back and forth. I'll go back to the slide done in the previous video. I'll come back to the slide of this current video. I'll go back to the slide of the previous video. You see, I'm just moving back. I'm just going back and forth. Now that's because the previous video or this video is tied to the previous video. Yeah, I think that's the better way to say it. That's the better way to say it. This video is tied to the previous video. The previous video we established the formulas and the ideas why we make use of those formulas. These videos, this present video, we just apply the formulas we've established in the previous video. Okay, so please do well to watch the previous video and then watch this one. Okay, even after watching this video, you can go back and watch the previous video again, so you know what's happening. Okay, so thanks a lot for watching, and thank you for your patience to watch this video till the end. Thank you very much, and of course comment, share, like, subscribe, and I'll see you in the next video. Bye for now.